Hey everybody, welcome back to my YouTube channel. If you're returning or if you're new, welcome to my YouTube channel. So today we are going to be doing, you guessed it from the title, SAT exponent questions. So exponent questions, I feel like they really do vary in terms of their difficulty. Some questions are easy, some questions can be really complicated. But with the tips that I'm going to show you in this video, you will be an Exponent Pro in absolutely no time. So without further ado, guys, let's jump into today's video. So let's begin first with this question right here that we have from practice test 1. So I first want to just discuss some terminology that I'll be referring to throughout this video, just so we're all on the same page. So when we have, I'm completely making up this example. These numbers are just coming from the top of my head. Let's say we have 5 to the third. We call this number right here, the 5, we call that the base. And then we call the little 3 right up here the exponent. So that's what we mean when we say the base and the exponent. So when it comes to exponent rules, we can only add or subtract the two exponents when they have identical bases. If their bases are not identical, we cannot go about adding or subtracting their exponents. So when we look at question 14, I can very clearly see here that these do not have the same base. 8 and 2 are not the same base. So we're going to have to do something to make them into the same base. So 8, we want to realize that 8 is actually a power of 2. So for example, if we have 2 squared, that's equal to 4. If we have 2 to the third, which as a reminder is just 2 times 2 times 2, that's equal to 8. So we can rewrite 8 in a way where it has 2 as the base, so then we can go ahead and manipulate what we have right here. So if we rewrite 8 as 2 to the third, and of course that's going to be to the x on the outside, and then we have 2 to the y on the bottom, we now have the same exact base. So this simplifies to 2 to the 3x over 2 to the y. So whenever we are dividing two exponents, which we're doing right here, what we do, we have the same base, so we're good to go. What we have to do is we're going to subtract the actual exponents. So 2 to the 3x divided by 2 to the y ends up giving us then 2 to the 3x minus y. We take the exponent associated with the base in the denominator and subtract that from the exponent as part of the numerator. So 2 to the 3x minus y. Well, that's a pretty coincidence we got going on here. Very beautiful coincidence, because they tell us right up here that 3x minus y is equal to 12. So 2 to the 3x minus y is the same as 2 raised to the 12th power, giving us then choice A. Next up, we have question number 7 from practice test 2. All right, so we can see that this question's a little bit different from the last one and that these both have the same base, so we can go ahead and subtract their exponents. So let's do that. So x raised to a squared, so x, we would do a squared minus b squared, because again, we said we subtract the exponent that's in the denominator from the exponent that's in the numerator. We know that that's equal to x to the 16. So we can see that they both have the same base here, x. So I'm going to then definitely have to start working with the exponents and set the a squared minus b squared equal to 16 to try to figure out what this is. Because I know that if x raised to this is equal to x raised to the 16, that a squared minus b squared then has got to be equal to 16. So let's go ahead and do that. A squared minus b squared is equal to 16. So this is obviously not related to exponents. This is a little bit of factoring, but a squared minus b squared, this is what we call the difference of perfect squares. I'm going to write that down. Difference of perfect squares. And the reason why we call it that is because a squared is, of course, a perfect square. It's just a times a. B squared is a perfect square, just b times b. So it's the difference meaning subtraction of perfect squares. So whenever we have the difference of perfect squares, we're going to do the first term here, so the a without the squared part, plus b times a minus b is equal to 16. All right, and you'll see that the reason why that gives you a squared minus b squared is when you go ahead and FOIL it, that will give you a squared minus ab plus ab minus b squared, and the middle terms here end up canceling out, so that just gives you the a squared minus b squared. All right, anyways, though, back to the problem. So we know then that a plus b times a minus b is equal to 16, and they were so kind, thank you to the SAT, they were so kind as to tell us in the question that a plus b is equal to 2. So 2 times a minus b is equal to 16, divide both sides by 2, we get then that a minus b is equal to 8, which gives us then choice A. Next, let's look at this gem of a question from practice test 7. Gem of a question. I gotta come up with some better intros. All right, so we can see that in this expression, we have some bases with a negative exponent associated with them. I am highlighting those in pink. And then we have 2 that are perfectly fine just with a positive exponent. So what does it mean when something has a negative exponent? Well, we typically don't want to express answers with negative exponents. So how do you make a negative exponent positive? Let me show you. So let's say you had, for example, 2 over, let's pick a good letter, 2 over a raised to the negative 5. Well, the way that you make a negative exponent positive is you take the base and the exponent and you flip it over the fraction bar. So this written as a positive exponent would just be 2a to the 5th. Let's say you had, 3b to the negative 3 over 4. You would go ahead and take the part that has the negative exponent, which is b to the negative 3rd here, and in order to make it positive, you would go ahead and flip it over the exponent bar. You only flip the part that has the negative exponent attached to it with the base. The 3 stays unchanged. So that becomes 3 over 4 b to the 3rd. So all you got to do is flip it over the fraction bar to go from negative to positive. So let's go ahead and do that with what we have here. We're going to have to move this x to the negative 2 to the bottom and this y to the negative 1 to the top to make both positive. So on the top we have y to the 1, which is the same as y, times y to the 1/2. And then at the bottom we have x squared then times x to the 1/3. So the top then becomes y times y to the 1/2 over x squared times x to the 1/3. So what we want to do then is realize that y to the 1/2 is the same thing as the square root of y. And then on the bottom, we have the x squared, and x to the 1/3 is the same thing as taking the cubed root of x. So the only choice that has that is going to be option D. I can make a whole separate video on how to convert from an exponent to the radical form, but basically the idea is this. Let's say you have, I'm making things up on the spot here, guys, obviously. Let's say you have x raised to the 4 over 5, and you want to express that as a radical form instead of an exponent. So I have this little saying that I like. Inner, upper, outer, under. So what that means then is that the upper number is going to go on the inside of the square root. So that's going to be x to the 4th. And then the number that's under is going to go on the outer part. So that would be to the 5th. So that's exactly why when you have y to the 1/2, it looks like this. There's a hidden 2 on the outside here. And then when you have x to the 1/3, there's a hidden 1 right here. And then the 3 goes on the outside. So that gives us choice D. Question 13. If a to the negative 1/2 equals x, what is a in terms of x? So a to the negative 1/2 is the same thing as a to the negative 1/2 over 1. You can write any number that doesn't look like a fraction as a fraction by just putting it over 1. And we know that that's equal to x. And as we just discussed in the last problem, you can go ahead and make this a positive exponent by flipping it over the fraction bar. So this then would become 1 over a to the 1/2 is equal to x. And as we said, a to the 1/2 is exactly the same thing as taking the square root of a, and that's equal to x. Well, if we want to get a alone, we're going to have to go ahead and square both sides because a is currently trapped under a square root sign, so square both sides. We get 1 over a is equal to x squared. All right, so now we want to get a alone. So we can do that by, there's one of two ways. So first thing you could do is multiply both sides by a. So if you multiply both sides by a, you'll realize then we get 1 is equal to x squared times a, and then you can divide both sides by x squared to get that a is equal to 1 over x squared. Alternatively, if you wanted to, you could have simply made this a fraction by putting it over 1, and then you could have just cross multiplied. Either way totally works here. So we get a is equal to 1 over x squared, which gives us choice C. So for question 12, we can see that we have exponents that are raised to another exponent, and that's set equal to some other exponent. So we're definitely going to have to set something equal here. So whenever we have exponents, like right over here, that are being raised to a power, what we're going to do is multiply each of the exponents by whatever the power is. So this is going to become x to the 2 times 1/2, and then y to the 3 times 1/2. And then the next set's going to be x to the 2 times 1/3 times y to the 3rd times 1/3, and then that's going to be equal to what we have over here on the right hand side. So let's just go ahead and simplify that. So this would just become 2 times 1/2 is just 1, so that's just x. Y would be y to the 3 over 2. This x would be, let's see, that would be x to the 2/3, and then this y, 3 times 1/3 is just equal to 1. I don't like how I wrote that 3. So that would just be y. Okay, so what we're now going to do is remember what we had said. Whenever the exponents have the exact same base, we're able to work with them. So whenever we're multiplying the exponents and their bases, we add them together. So before, when we divided, we subtract, but when we multiply, we add. So let's go ahead and do that. So we're going to have to get common denominators here. Of course, the SAT never gives us an easy question, right? So x, we can rewrite this as 3 over 3 because we want to get them both to have a common denominator. And y, we can rewrite as 2 over 2 because we want that to have a common denominator with the other y. So that then becomes x to, we're going to add up the numerators to the 5 over 3 times y to the 5 over 2. And we know that that's equal to x to the a over 3 times y to the a over 2. So how ironic that it just ends up perfectly matching on both sides. Wink. I can't wink, but I'm doing my best. So a over 2. All right, so they're asking us what is the value of a. Well, the value of a is exactly the same for both of these. We know that it's equal to 5, so that means the choice C is correct. Alrighty, and as promised, I saved the craziest, the most difficult exponent question for last. So let's go ahead and give this one a shot. So they want to know what's the same as 9 raised to the 3 over 4. So actually at first this looks pretty reasonable, but just wait, it's going to get bad. So what that means then, as we've talked about, the number on the top, that goes with the inner part, and the number on the bottom goes with the outer part. So we can go ahead and rewrite this as 9 to the 3rd, and on the outside, we're going to put the 4. As we said, the expression was upper, inner, under, outer. All right, so this looks great, but that doesn't match any of the choices, of course. Why would it? So let's go ahead and try to break this down. So 9 to the 3rd is the same thing as 9 times 9 times 9, and that's to the 4th over here. And 9 is actually a perfect square, so if we so desired, we could actually break this down further. So each 9 is going to basically fork out into 2 3s multiplied by each other. So I'm just writing that here, and then we'll write that in a neater form, of course, in the later step. So that's going to give us 6 threes. So 3 times 3 times 3 times 3 times 3 times 3. What a tongue twister. So many threes. So we can see that this is basically 3 raised to the 1, 2, 3, 4, 5, 6. 3 raised to the 6th power. We can rewrite this as. And that's going to be raised to the 4th. So as we said, when we multiply two exponents, we add the actual exponents together. So 3 raised to the 6th can alternatively be rewritten as 3 raised to the 4th times 3 squared. So what that would give us then, so 3 raised to the 4th, if we take the cube root of that, that's just going to give us 3. And then 3 squared to the 4th, that would then give us 3 to the 2 over 4, which is the same thing as 3 times 3 to the 1/2. And as we said, 1/2 just means the square root. So 3 times the square root of 3, which ends up giving us choice D. So I would just like to stress this is absolutely a pretty crazy question to make all of these realizations. So again, this is only for like upper level, scorers here. So I wouldn't say to stress out about a question like this. As long as you kind of understand how I broke it down, that's really what matters for this question. Thank you so much for watching. If you enjoyed this video, make sure to give a big thumbs up and also subscribe. Drop me any very kind, thoughtful comments below as well. Love support from you guys, of course. And just as a reminder, all of our crash courses and our SAT math workbook, No BS SAT math, that's all linked in the description below. Make sure also to follow me on TikTok. Testprep Tips is my username. I post daily tips and tricks on there for the SAT and the ACT. Again, guys, thanks for watching. Take care. Have a good one.